My name is Elliot Chu, and I'm the Interim Dean of the College of Science at the University of Arizona. Today's lecture is called Water, Society, and a Changing Climate. Our lecturer is Kevin Andriukaitis, who came to the University of Arizona in 2015. Kevin is a graduate of our Geosciences program, where he received a PhD. He is currently an associate professor in the School of Geography and the Department of Geosciences here at the University of Arizona. He is also chair of the Graduate Interdisciplinary Program in Global Change. Kevin's talk will concentrate on the impact of climate change and how it will result in too much and too little water. And we believe this will be society's biggest challenge in the near future. His talk will concentrate on impacts of water on past civilizations and how it will help us chart our pathway forward.
I'm Kevin Andriukaitis. I'm an associate professor of Earth Systems Geography in the School of Geography, Development, and Environment, and the Laboratory of Tree Ring Research here at the University of Arizona. In this final talk in our series, we explore the connection between climate, water, and human society. How does variability in the planet's water cycle influence our civilization, past, present, and future? And what lessons can we learn to avoid the worst consequences of climate change? Over the past weeks, we've learned about water in our solar system and what it reveals about the origin and evolution of our own water planet. We've learned how the vast expanses of water that are our oceans have varied over time, how human activities are causing seas to rise, the oceans become more acidic, and the very rhythms of the ocean to change. We've seen how in search of water, that human society has sought it in rivers and even under our own feet. And we've asked, how sustainable is this use of water? And today we'll see what determines whether our society is vulnerable or resilient in the face of climate extremes and climate change. When it comes to the challenges that we face from climate and water, it's both a story of too little water, of drought, drying, rivers running low, and the demands of a warming atmosphere, and of too much water, of floods and strong storms, rising seas, and increasingly extreme rainfall events. Indeed, it is on issues of water, of too much and too little water, that we face the greatest challenges of climate change. And as you'll see today, in many places, we're already seeing and facing these very challenges. So how are we changing the climate, and what does global warming have to do with water? Climate scientists have long recognized that increasing the amount of carbon dioxide in the atmosphere, mostly through the burning of fossil fuels like coal and oil and gas, increases the amount of energy trapped in the Earth system, which increases the temperature of the planet, warms the oceans, warms the land, and warms the atmosphere. So how does this warming atmosphere alter our planet's water cycle? Well, as our atmosphere warms, the amount of water it can hold as vapor increases. In some regions, this leads to more intense storms and greater rainfall, while in other regions, the warm atmosphere's demand for water from the surface leads to more evaporation and the desiccation of the land and more severe droughts. But even over regions that are normally dry, global warming brings more intense storms and floods. And over wet regions, it can cause severe dry periods, even over places like tropical rainforests. Precipitation varies naturally as well. Wet years and dry years have come and gone through the centuries, and these provide evidence of how variable our climate system really can be. But climate change introduces additional challenges. It creates long-term trends towards drying in regions like the western US, the Mediterranean, and southern South America. It intensifies the patterns of extreme events. Droughts become even drier. Floods become even more severe. And if droughts or floods like those that happened in the past were to occur today, they would be even more intense and the consequences even more severe. Our fundamental physical and scientific understanding of the Earth system lets us predict these future changes. But the past also provides us with a chance to test the models we use to forecast the future and to see how past civilizations have adapted to, or not, times of too much water or too little water. And this is critical. What we know from even just recent events is that what turns a climate hazard, too much water or too little water, into a disaster is how vulnerable or resilient our human society is. How robust and flexible our infrastructure, our economy, our society, our governance are. How we prepare for and respond to challenges of extreme events determines whether we thrive or whether we suffer. Because humans are not simply passive victims of too much or too little water. What decides whether we prosper or we collapse reflects our planning, our creativity, our innovation, our ingenuity, our foresight, and our cooperation with each other. So today I'd like to take us on a tour through both space and time to see how climate and human society have interacted in the past, the present, and then what this reveals about what our future may hold. What is it that determines whether too much or too little water is too much for our society to bear? So our first stop on this tour will be Southeast Asia, where we'll hear how the amazing hydrological civilization of the Khmer Empire and the city of Greater Angkor survived past climate extremes and what may have caused their ultimate demise, and also what we expect for future challenges in this region. Then we'll return here to the western United States and look at simultaneous challenges of both too much and too little water, of drought and of flood, past, in the present, and also looking to the future. So here's our first stop. The Khmer Empire controlled large parts of Southeast Asia for more than 6 centuries, starting in the 9th century of the Common Era. They started to build this vast and complex city of Greater Angkor, which is in modern-day Cambodia. And in size and innovation, this city exceeded any of its contemporaries anywhere in the world. And really the most incredible features of this hydraulic city were the intricate networks of reservoirs and canals they built to manage the variability in the annual monsoon rainfall. The Khmer constructed the system to deal both with situations of too much water, which could destroy both infrastructure and agriculture early in the growing season, and situations of too little water, where drought or monsoon failure or a late monsoon could endanger the entire rice crop that sustained millions of people on this landscape. This map of Greater Angkor from archaeologist Damien Evans gives you an idea of how extensive the city and its water infrastructure really were. Zooming in on even a small section, like this here, reveals a diverse network of pools, reservoirs, canals, channels, all dedicated to moving water off the landscape in times of too much water, or providing it in times of too little. Greater Angkor is believed to have finally met its demise in 1431 in the Common Era. What exactly caused this supposed collapse is still subject to a lot of debate. Was it foreign invasion, a shifting of regional political or economic activity, or did climate change play a role in the end of this city that was tied so closely to managing water? Well, a decade ago, we set out to test this final idea and determine the potential role of climate in the demise of the Khmer Empire at Angkor. Now, because we don't have weather records of past rainfall or stations from the 15th century that tell us about precipitation and temperature, we instead turn to the annual rings of trees. Now, we were fortunate with our Vietnamese colleagues and collaborators to discover that these trees here, the Fujian cypress, growing in the southern central highlands of Vietnam, not far from Angkor, could actually live to be more than 1,000 years old, and that their rings could tell us about the amount of rainfall each and every year going back into the past. Now, a few weeks ago, my colleague Connie Woodhouse already talked about how we can use the annual rings of trees to quantify or reconstruct past climates, even before we've got weather observations. First, we extract tiny cores no wider than a pencil from these trees. This does the trees no harm, but it reveals that these trees have annual rings, annual growth rings. Now, even here, sitting on my dirty fingers, you can see that the pattern of wide and narrow rings we use to study past rainfall is evident. Now, these wide rings, like you see here, reveal periods of abundant water and even flooding, while where those rings are narrow, these are times where it was severe and extended drought or a failed monsoon. If these happen for year after year after year, we call these megadroughts. Now, we take these core samples from lots of trees. We surface them until we can visualize the individual cells in each ring. We date each ring to its exact year of formation, and then we measure them, hundreds of thousands of individual rings. By combining these data, it gives us a picture of tree growth going back through time. So what you see here is a record of the average growth from these trees in Vietnam, showing periods of rapid growth and presumably lots of water, and periods of slower growth and persistent dry conditions. We can then use data to develop statistical models combined with recent weather data to reconstruct what happened in the past. Rainfall, soil moisture, temperature, and even the amount of snow going back through time, year by year by year. If we can do this at 100 different forests around a region like we did in Asia, we can even map the pattern of annual drought or flood in space, in effect creating maps of past climate, again, year by year by year. Now, instead of just reconstructing rainfall, we use a metric called the Palmer Drought Severity Index, which incorporates not just the amount of precipitation, but also the loss of water from the soil due to evaporation and the storage of water within the soil that lasts for months at a time. This allows us to say whether conditions at any location are abnormally wet or abnormally dry. A 0 would be normal, positive values tell us it was unusually wet, and a negative values tells us it was abnormally dry. So when we examined our maps of reconstructed drought in the past, what we found was that the demise of Angkor in 1431 was preceded by 2 periods of mega drought in the middle 1300s and then again in the early 1400s, with a brief but intense period of flooding right around the year 1400. In our paper a decade ago, we concluded that it was these droughts, which we named Angkor I and Angkor II, that contributed to the end of the Khmer Empire at Angkor. In the years since, we've gained a better insight both into the climate and archaeology of Greater Angkor. What we now know from tree rings was that the Khmer weathered previous periods of both too much and too little water in the 12th and the 13th century. But we also know that through time, the water infrastructure that they had built started to fall into disrepair. Flooding in the late 1100s corresponded with a rapid decline in the capacity of these canals and reservoirs and started a steady decline that lasted until 1431 and the end of the empire. The two Angkor droughts occurred during a period where the water network was only functioning at 20% or less of its capacity. But we also have reason to think that the flooding played a major role as well. So I want to show you one example of how climate and the decline of infrastructure may have manifested itself as Angkor slid into its demise. This map you're looking at shows a LiDAR image. Now, LiDAR works a little like radar, but uses laser light instead. It actually allows us to look beneath the modern landscape. We can peel back the vegetation and see the ancient structure of the city below. This part of the city that you're looking at was essentially downtown. You can see the major administrative and governing center of Angkor Thom and the religious center of Angkor Wat. So this part of the city was absolutely central to the Khmer Empire. Let me call your attention to that black box just off to one side of Angkor Thom. That's where we're going to zoom into. And what do we see here? Right in the middle of everything is evidence of rapid flood damage that was never repaired. Indeed, there's evidence throughout Angkor that the water network declined, fell into disrepair, or was altered over centuries. Thus, the demise of Greater Angkor wasn't simply because there was too little or too much water, but rather that the system that the Khmer had built to adapt to climate extremes like those declined, and they suddenly became vulnerable to these extremes that they might have survived in earlier times. The archaeologist Bernard Grossier put it this way, that the same water infrastructure that had allowed the flourishing of this empire ultimately, in its decline and disrepair and abandonment, led to its own asphyxiation, as he said. Now, what about today in Southeast Asia? We see similar challenges from periods of too little and too much water. For instance, in 2001, when I was in Bangkok, the city was devastated by floods that hit Thailand, in fact, flooding large parts of the city itself. These floods even closed the airport. Amongst other things, these floods had a severe impact on Thailand's rice crop. And because Thailand's a major exporter, these consequences rippled out through our modern, interconnected world. Too much water in one place, leading to too little food in others. Climate scientists believe that there are more such events like this in our future due to climate change. One recent study even estimated a 761% increase in economic risk from floods in the region by the end of this century. And this was not only from climate change, but rather by the increasing exposure of populations in floodplains and living along rivers. Not only will rainfall patterns get more intense and society more vulnerable, but in Southeast Asia, we're also concerned about the increasing strength and the rainfall amounts that come with tropical cyclones, and this itself will lead to more flooding. Now, for the second and final part of our tour, I want to return to the Western United States. Here in our part of the world, we also have amazing trees that can tell us about past climate in their annual rings. These bristlecone pines that you're looking at can live for nearly 5,000 years, and the deadwood you can see in this picture on the ground can take us back even further, as my colleague Connie Woodhouse showed in her presentation. From trees like these, we know that severe droughts can occur naturally in our part of the world. In the late 13th century, one such mega drought struck the Four Corners region. Imagine if such an event were to happen today with the additional influence of climate change on top of this. Human society in the Southwest at the time was vulnerable to these droughts. They responded in a number of ways, including migrating away and abandoning parts of the region. But I want to talk about a much more recent drought, the one that California experienced starting in 2011, and still, by some measures, continues through today. The drought started with several years of reduced rainfall, culminating in the most severe year of that drought in 2014. In that summer, Southern and Central California had their lowest soil moisture levels on record, and the highest temperatures since formal record keeping had begun. This drought dried reservoirs and rivers, killed millions of trees across the strait, stressed the water delivery infrastructure to its breaking point. But my colleague Dan Griffin and I were curious. Was this drought actually unusually severe in the context of the past? Or was it like droughts that occurred in the past, like the Great Drought of the 13th century we just looked at? So we set out to find out by once again turning to the trees and their rings. Specifically, these magnificent blue oak trees whose rings are sensitive to winter precipitation in California. When we reconstructed precipitation back into time, this is what we found. Our trees actually matched rainfall observations really well, and so we were able to reconstruct precipitation back into the 13th century with a great degree of confidence. But when we compare the current drought to past rainfall deficits, we actually find that the current drought wasn't exceptional. Sure, it was low, but not out of the historical range. But what about soil moisture, that PDSI metric I mentioned earlier? Well, here, in order to do a reconstruction, we need a much wider variety of trees, like these from the higher elevations of the mountains in California. But once again, our reconstruction matches observations really well. But this time, when we compare the current drought to past droughts over the last 1,000 years, we found that this drought was unusual and exceptional, one of, if not the most severe droughts of the entire last millennium. So how do we explain these two different results? What California was experiencing was what we call a hot drought. Record high temperatures increased the atmosphere's demand for moisture, drying out soils and exacerbating those rainfall deficits. Unfortunately, we expect these types of droughts, which some have called global warming droughts, to become more severe in the future. But the future is now here in the western United States. Indeed, my colleague Park Williams has shown that the current drought across the West that we're experiencing here in Tucson and elsewhere across the region, which has actually been ongoing since the early 2000s, is the second worst drought over the entire region over the last millennium, and that this severity is also driven, as the California drought was, by higher temperatures. A southwestern United States hot drought that's also affecting snow and stream flow, as my colleague Connie Woodhouse described. What happened in California after that unusual and exceptional year of 2014? Well, after a few more years of hot and dry conditions, the drought quite suddenly reversed. Something climate scientist Daniel Swain has called whiplash. A series of severe storms at least temporarily brought the drought to an end. Indeed, once dry reservoirs nearly overflowed, like the near catastrophe here at Oroville Dam. But even with this event, human activity played multiple roles in exacerbating this. Climate change possibly contributed to the severe spring storms, but inadequate planning and investment in infrastructure and increasing exposure to climate hazards combined to make this event the near catastrophe that it was. This isn't the first time California has been inundated by heavy rains. Tree rings once again tell us about the floods of, in this case, 1862, when cities and farmlands around the state were flooded by torrential rainfall. What might a similar event look like today, though, with rainfall made even more severe by climate change? Even the U.S. Geological Survey is planning for such an event to try and anticipate and prevent the worst consequences of this, something they call the arc storm. Because we anticipate that these kind of conditions will only become more intense in future. The whiplash between too much water and too little water made more extreme by human-caused climate change. But once again, it's important to remember we're not passive victims in the face of extreme climate. Our future's in our hands. Which pathway we follow, how severe future climate change will be, how large the extremes of too little or too much water really become, depends on how much carbon dioxide we emit to the atmosphere, how warm the climate gets, and how much the water cycle changes. That pathway, the one we follow, is ultimately up to us. So one thing we need to do to avoid the worst consequences for human society is actually avoid those scenarios where we emit a lot of carbon dioxide. That means expanding renewable energy, reducing deforestation, and working to develop new technology to actually capture atmospheric CO2. But we've seen today we're already experiencing some climate change, and at least some additional change is coming no matter what we do. We need therefore to also work to make our communities less vulnerable, to adapt to changing conditions of too much and too little water, to ensure agriculture can sustain our societies, and to maintain and adapt our infrastructure and our planning to this new normal of climate change impacts. How water on this planet changes, how much we use from our rivers, how much we extract from groundwater, how high the seas rise, how severe storms become, and how widely drought impacts our economies and our societies is in our hands. This is a water planet. This is our planet, and we've got a lot of work to do together.
Thank you for joining us for the fifth and final lecture in our series on water. We hope you enjoyed the 2021 University of Arizona College of Science lecture series. To learn more about the College of Science and our incredible research, please visit science.arizona.edu. Thank you to our presenting sponsor, Tucson Electric Power, and our series sponsors, Cox Communications, Hale'ulo Companies, Raytheon Missiles and Defense, Research Corporation for Science Advancement, Tucson Medical Center, and Visit Tucson.
Your generous support is what makes this series possible.